Hey, good morning again, team. Chemistry coach coming at ya. So we hit kinetic molecular theory kind of out of order. The other video or the prior video, if you're watching them in order, like you should, but I guess you don't have to because I'm not going in the order of a lot of things. I'm just going with what seems to fit the story the best, and that's okay. What was introduced in kinetic molecular theory after we did looked at the postulates and looked at kinetic energies and all that fun stuff and pressure, what that really means, impulse times collision frequency. You saw volume get pulled out of that, you saw temperature had an impact. So it kind of summarizes down to four main properties or parameters of a gas that really determine a gas's overall behavior. Right? You probably figured this out already. We'll just list it up officially now. So volume, of course, came into play. When we get to all of the gas laws, you'll see these kind of pan out. So the volume of whatever container it is, remember we're making the assumption that the volume of the gas particles are so tiny they're insignificant compared to the volume of the container. We're assuming the volume of the gas particles is zero for an ideal gas, right? If we actually account for the gas particle volume, we can't use the ideal gas equation anymore. Temperature, of course, huge impact on collision theory because you increase temperature, particles are moving faster, they're hitting with more force, there's more impulse. Woohoo! So that's going to be a big one. Temperature is going to haunt us, and you'll find that the majority of the problems that we do quantitatively with the mathematics of gas laws will be in Kelvin temperature, right? So you're going to be constantly converting. We measure it in degrees Celsius, got to convert it to Kelvin, add the 273.15. You're going to do that a lot. The number of gas particles, obviously, that has a big impact on the collision frequency. More particles, more collisions. Oh, right? So we're going to do that in terms of moles because usually there's lots of particles in a gas, like more than two. Right? We're going to use moles or little n for that. And then pressure is kind of the big one. I mean, you're all familiar with volume, temperature, and number of particles. Pressure is kind of that new one. We introduced it in the postulates of kinetic molecular theory, and again, defined that as the impulse times the collision frequency. So what I want to do is just we don't need to spend time on volume, temperature, and number of particles. I think that's self-explanatory. So let's spend a little video reviewing what we learned in kinetic molecular theory about pressure, some units that we use for pressure. Oh my gosh, there's a lot of units. That and solution concentration, just tons of units for those two parameters of matter. And then a big one on, what's atmospheric pressure. A lot of us throw that word around every day, how that's affected by altitude. If you're mountain climbing, you know what I mean. You know what I mean. I can't breathe. And then we'll look at measuring pressure, right? Measuring atmospheric pressure, measuring pressures of gases using barometers, manometers, All right, gang, let's take a look. There's a lot of units for pressure. So let's start with I guess the best one, but the least used and most awkward one is the SI unit for pressure, right? The dreaded Pascal, which we defined or derived in kinetic molecular theory. Remember, from kinetic molecular theory, we derived the fact that pressure is the impulse, the transfer of momentum, right, of a particle colliding against the surface, times the number of times these particles collide, the collision frequency. And then we related that to force over unit area, right? The harder it hits, blah, blah, blah. So if you go through the derivations from KMT, you get a Pascal with the SI unit of newtons per, there's your force, newtons, and the area is meters squared. So, 1 Newton per 1 meter squared, that's a Pascal. And if you plug in the units in there, you'll get kilograms per meter second squared. Very awkward unit to use. I don't know anybody who uses that one. It's not really practical. It's great for, theoretical calculations and all that fun stuff, but not practical. So what we want to do is get a different unit that's less awkward. And let's define a reference point. And that reference point is going to be the atmospheric pressure at sea level, the surrounding atmosphere. We'll look at that in the next board. So think of atmospheric pressure as the pressure of all the gas particles in the atmosphere and their collisions on a surface. So what is, like at the surface, if you take a column of air, above that, what's the combined pressure from all those particles? Well, it depends on what altitude you're at, right? So we have to define a particular altitude, and we define sea level as that. So let's look at that. So atmospheric pressure in general is just a term of the the pressure of the particles above you in a column, right? So let's take a look at the effect of altitude on that. And then we're going to use the pressure at sea level. Atmospheric pressure at sea level is kind of a common reference point to look at all of the other units. Let's take a look at this. Let's take a look at my horrendous Pictionary skills here. Although again, Pictionary is just psychic connection, right? You can draw anything. If you got a psychic connection with your partner, you'll get it, right? So let's imagine we got somebody at sea level, like my person there. So we're at sea level here. And if you're into hiking or mountain climbing or something like that, when you go up to a higher altitude, how far you are above, sea level, it gets harder to breathe. If I ever go to Big Bear, we're only a couple hours from Big Bear. We stayed up there for a week once. I'd be always like short of breath. I'd breathe in deep and I'd still be like, I just can't feel like I can get a full breath of air. And I'd move around slower. You hear about people up on top of mountains. They'd be like, on top of Mount Everest, climbing Mount Everest, you take a step, breathe, freeze your lungs, take a step, because you're just not getting enough oxygen, all right? Would you agree that at sea level, you've got this column of air pushing down on you, right? Like the weight of the air molecules pushing down on you. Well, that's the pressure. That's what we call atmospheric pressure. But if you go up higher, there's less total particles of air, fewer gas particles. So that weight you would feel is less, right? Now, the percentage of oxygen is still 21% here versus up on top of a mountain. Problem is, if you've got fewer gas particles up here, 21% of a smaller number is less oxygen per breath. That's why when you breathe up on top of a mountain, you're not getting as many oxygen molecules, which is harder for your body. For something like me, I'm like, I always feel short of breath. Right? And sometimes you'll get, I'm not a cyclist, I was a sprinter, but I've heard stories of cyclists go train at higher altitudes for however long they take. And I guess their body, I'm not a physiologist or anything like that or biologist, but I guess your body's able to produce more red blood cells to deal with the less amount of oxygen up there. And if you do that for a while, now you're able to utilize less oxygen better. I don't know what I'm talking about, right? And then what you go down is compete at the lower sea level, right, or a lower altitude, and you have more oxygen capacity than someone who may be trained down here. Or for something, I followed Peyton Manning for a long time when he went from the Colts to the Broncos. I was like, but then I started like the Broncos, and that's Mile High City, right? They seem to always have an advantage in the fourth quarter because the other team the defense would be gassed by the fourth quarter. There's less oxygen up at the higher altitude. They're right? So pound the ball, so they'd be just smash into them. Until they got Peyton Manning, of course. They were a big running team. And then Peyton Manning, woo! Right? You just pound them. The other team would get more tired because the Broncos are training at a higher altitude. They can utilize oxygen better. But anyway, I think you get the idea, right? Atmospheric pressure is going to be lower as you go higher. So just something to keep in mind. So let's pick a reference point of sea level. All right. So at sea level, the atmospheric pressure, now, whenever we say atmospheric pressure, or I do, we're going to assume sea level unless otherwise specified. Good. So at sea level, atmospheric pressure is 101,325 pascals. Oh, what an awkward number, right? So let's define that as 1 atm. So that's the new pressure unit, right? That's called atmospheres. That is by far the most common unit you'll hear people use is atmospheres. We're going to deal with that a lot. But there's a lot more units we got to get through. Now, to get to the other units, let's talk about measuring atmospheric pressure. And that's going to lead us into some of the other pressure units as well. So let's take a look at the infamous barometer. Now, one thing you might have run into in movies or something like that, or personally yourself, is if there's a pressure difference. Gases don't like pressure differences, right? So if you've got a pressure differential, gases will flow from higher pressure to lower pressure. So you might want to write that down. So gas flow, let's say gas particles. So let's put gas particles. I wasn't going to write this down, but I think you're aware of this. flow from higher pressure regions to lower pressure. So that's kind of an aside, has nothing to do with this. But if you go up in an airplane, right, they pressurize the cabin, correct? It'd be a bummer to go up to 20,000 feet and they don't pressurize the cabin. You're like, having a hard time breathing, right? But if something happens, you've seen movies like this, Live, World War Z, that one where Tom Hanks crashes down. I forget it was on that island or whatever. I forget the name of that one, where something happens to the plane and the door blows out or a window goes out or the back half of the plane goes out, because you got a higher pressure in the airplane, right? So if that opens up, everything goes pushing out, trying to equalize those pressures. So yeah, you get some interesting results from that. But just remember, gases flow from higher pressure regions to lower pressure regions. And if you study meteorology, you'll start to understand where wind comes from. Let's all give thanks to Evangelista Torricelli, way back in 1643. That's pretty insane. I mean, just to me, even thinking about science back then, just trying to survive back then, I think would be difficult. Measuring atmospheric pressure. He's the first one to kind of, measuring the force per unit area of gas particles is pretty hard to do. For liquids, it's a little bit easier. So he was able to devise this creation, right? A pretty simple creation to measure the pressure of the gases of the atmosphere relative to the pressure of a liquid, which could obviously be calculated. So for example, we can take any liquid, but I found mercury worked really good because it's really dense. We'll compare it to water in a second. But he invented a barometer. So a thermometer measures temperature, a barometer measures atmospheric pressure, right? But not the pressure of a specific gas, of atmospheric pressure. So imagine you got this vat of liquid mercury. Yay, don't drink it. And the atmospheric pressure is pushing upon the surface of that liquid mercury. Well, let's take a sealed on one end tube filled with liquid mercury and invert it. You ever done that where you fill a test tube full of liquid water? And then you can put a little piece of paper on the top and you can invert it and no air bubbles get in there. And then you could put it into a beaker of water and put it over like a piece of calcium and gather all the gas and collect the gas by displacing the water. That's a lot of fun. But imagine you take that tube of liquid mercury and go bloop, and get it inside there. Well, what happens, that liquid drops, all right? And it drops depending on whatever the pressure of the atmosphere is. So depending on if the higher the pressure of the atmosphere, it doesn't drop as much. If the force of this is less, this is going to drop more. What happens is it drops until the pressure of the gases of the atmosphere equals the pressure of the liquid pushing down. See that? And you can calculate it if you want to. We're not going to in this class. But the pressure of the liquid is just the gravitational acceleration, right? Times the density of the liquid, so it's dependent on the density, times the height of that column, right? The higher the column, the more dense it is, the more weight is pushing down. So I just define those. But when those are equal to each other, that level of mercury stays at a constant height. And if you change your altitude, that changes the atmospheric pressure, changes this. But if we're at 1 atmosphere, right, at sea level, if we're at sea level, he found that this pushed up. Now, he didn't know what an atmosphere was at the time, or a Pascal. He found that, he originally did it in inches of mercury, but, well, we don't like the English units. We'll find that this is 760 millimeters of mercury at sea level. You go, oh, okay. Problem is, if you used water's a little over 13 times less dense than mercury. Oh, I think like 13.6 times or something. So if you wanted to use a barometer of like pure water, it'd be like over 10 meters tall. It would go out the roof of this room. You'd be like carrying this big old barometer around like, oh, this is not working. I can, pole vault with it. Yeah, that'd work. You got a pole vault / barometer. Get rid of it. So mercury works because it's a really highly dense liquid. So you might, maybe have a meter high barometer, which we have in our lab. Well, I'll have a video in lab on how to use those barometers and measure atmospheric pressure specifically. Correcting for where you are on the planet, temperature, all those kinds of things. But for now, sea level, that pressure, again, by definition, was 101,325 pascals. Well, it turned out it pushes up a column, actually settles at a column of liquid mercury of 760 millimeters mercury. So can you see a relation now between atmospheres, pascals, and a new unit, millimeters mercury, huh? But pretty simple concept for a barometer, I think. Now, if we went up to Big Bear, climbed up, went up a couple thousand feet, this pressure would reduce, which means this column would come down. You would need less liquid water to balance that out. So that would change. So if we went to a different pressure, this would drop down. So if we went to here, this would be a higher altitude. Whoops, if I could spell. Right, so if we went to a higher altitude, that would drop down a little bit. So it'd be less than 760. I've actually seen in lab, pressure fronts come by, like a storm coming in. You can see the barometer drop as the storm's coming by. It's kind of cool. Right? So this gives us a new unit that I'll write on the next board. Hey, that's by far the most common in lab, millimeters mercury. Yay for the barometer! There we go. Now we got a new board. So we've got this new pressure unit, millimeter mercury, very, very, by far the most common in lab. But let's honor Torricelli, right? So that's going to be equal to a torr. A lot of people capitalize that. I've seen it lowercase capitalized. So if you're honoring Torricelli, you probably should capitalize it, but most people use the lowercase t. I don't care. Right? So millimeter mercury is a torr. So if we're at sea level, right, then 1 atmosphere at sea level, 101,325 pascals, would equal, remember that went up 760 millimeters mercury, or torr, right? They're not quite exactly the same, but out to so many decimal places, they're equivalently the same. So we'll put an approximately here. But we're going to treat those as exact numbers in this class. They go out to so many decimal places. So now we got our lab units. So these are common for lab, right? So you will measure things, and then to do gas law calculations, you'll probably have to convert that to atmospheres using the 760 to 1 conversion. We tend to avoid pascals as much as we can in calculations. All right. There's a couple other weird units you've probably heard before that we don't really use necessarily. So I'll write these up. So other pressure units used. If you watch the news, I'm not a big news guy, but I remember as a kid, my parents would have the news on. You didn't only had a couple channels, or you didn't have a lot of choices what to watch. And there'd always be the weather report, and they'd be talking about pressure, low pressure. I didn't understand it and stuff, but they'd be talking, this is so many millibars, and this is so many millibars. And I'm like, what's a millibar, right? Is that a mini bar? Is it a millibar? I don't know. So you'll get this bar term, which is common. The infamous bar, which is what the International Union of Pure and Applied Chemistry is trying to get us to go to. A bar is about an atmosphere, right? It's about an atmosphere. Not quite, but commonly they're treated as the same. But if you want to look at it, 1 atmosphere, if you want the technical correction, is 1.01325 bar. Pretty close, but if we interchange these equivalently, you're going to be off by a small amount, right? So atmospheres is what we've been using this most of our careers, right? The IUPAC is trying to push us to use bars, and most of us are resisting that, right? It's just like, oh, come on, the change is almost irrelevant. Oh man. Now, my guess is, if you're not a chemist or a physicist or something like that, you're out there, you're filling up your tires. It doesn't say to fill them to so many pascal or kilopascal or millibar. It says pounds per square inch, right? Gotta love those English units there. Pounds per square inch, or PSI. Not that we're going to be doing anything in PSI, but if you're curious, 1 atmosphere is 14.69 PSI. So if you're ever looking to convert from really wacky English units into ones that are useful for us, hey, there you go. Not that big a deal. So we've got the SI units of Pascal, commonly use kilopascals. So instead of 101,325, they use 101.325 kilopascals is one atmosphere. Atmosphere is by far the most common, pushing us to use bar. All right, so I'm going to avoid bar. I'm going to keep with the atmospheres. And then millimeters mercury, torr, very, very common. All right. So we know how to measure the pressure of the atmosphere using a barometer. Pretty simple, right? What if we have a gas like in a flask or something sealed off from the atmosphere? If my flask is this big, how am I going to get the barometer inside the flask? It doesn't work, right? So barometers are useful for atmospheric pressure, but not for like a gas pressure. You can't get the barometer. I guess if you could get a little barometer inside it, but it's not going to happen realistically. So we need a different device to measure actual gas pressures. And that's the manometer. And every time I hear that, I want to go manometer, manometer. Is that from the Muppets or something? I can't remember. Let's look at manometers. All right, manometers are kind of weird at first, but I think the concept is fairly straightforward. I think most students end up getting a gut feeling for it, and once you get that gut feeling, the calculation's pretty straightforward. So let's say we've got a gas sample in a flask. Can't stick a barometer in there, right? Pretty easy to do. You could actually make this yourself. Just get some glass tubing, heat it up, bend it. Make sure you watch my video on glass work and safety. Let's have a little stopcock here so we can, contain the pressure. And just make this little, kind of a YouTube. On YouTube. You're seeing a YouTube on YouTube. All right, anyway. Just self-entertainment. It makes you live longer, right? And you can put any liquid you want in there. But let's just say we have liquid mercury. If you have something other than liquid mercury, it creates an extra issue in your calculations. Because remember, we're going to compare this to atmospheric pressure we're doing it relative to atmospheric pressure, which is going to be measured with a barometer that has liquid mercury. So ideally, you have liquid mercury in here, so you have apples versus apples. If you have any other liquid in there that's a different density than mercury, you got to make a correction to something. We're going to do that in lab. I'm not going to do that to you on an exam or something like that. All right, we'll talk about that in a little bit. So let's put some liquid mercury in there. Would you agree that if I can spell correctly, woohoo, the atmosphere, if this is open to the atmosphere, then the pressure of the gases are pushing. So that's atmospheric pressure pushing on there, which we can measure with a barometer, right? So that's measured by a barometer. Which we showed you how to, and in lab we'll show you the specifics on how to do it. Really, it's just how high is that column of mercury. And would you agree, if I open this stopcock, then this gas travels through, and then you have the pressure of the gas pushing on this side. Assume this is the same diameter all the way through. It's hard to draw when you're doing it like that. So it's kind of like a reverse tug of war, more like sumo wrestler, pushing against each other. You got the pressure of the atmosphere pushing down here. You got the pressure of the gas pushing down there. They're both pushing down. They're pushing, and the gas is pushing on this side of Mercury, and the atmosphere is pushing on this side of Mercury. So you got this fight between the two pressures, right? If those two pressures are exactly the same, they cancel each other out, and they'll end up being at the same height, right? But what if the gas is higher pressure? It pushes the liquid down. So the liquid's lower on the gas side. What if the gas is lower pressure in the atmosphere? The atmosphere pushes harder and it's lower on the atmosphere side. So you can kind of get a gut feel for whether your gas is higher or lower or equal to atmospheric pressure. I'll put up a couple more pictures on the next board to show you if it's lower or higher. But in this scenario, would you agree that if the heights are equal, right? So if we have equal heights, then the pressure of the gas is equal to atmospheric pressure measured by the barometer. Nice. We'll do one lab in my class where we do that experimentally, where we, play with the experiment and equalize the pressures. And we're going to do another one where we don't do that. We're going to have a height difference, so we have to account for it using kind of an internal manometer built into our system. Let's look at scenarios where, this is kind of boring. What if this is lower or higher? Oh. All right, here's our two other scenarios. There's only three scenarios. Either the heights are the same on both sides, or it's lower on the gas sample side, or higher on the gas sample side. Let's use our guts to see if our gas is higher or lower than atmospheric pressure. So think about what's going on in this system. Would you agree, let's use purple for this, that the atmosphere is pushing down here in both scenarios, right? Now let's move this down. So on the open end side, atmospheric pressure is pushing down on there, which is measured by a barometer, right? Now over here, just like before, we open up the stopcock, the gas travels through, and then we got the pressure of the gas pushing down there. Open up the stopcock over here, we got the pressure of the gas pushing there. So again, you've got this reverse tug of war of the atmosphere here, the gas here, pushing. Now look at this one. Would you agree? Which one's pushing harder? The gas is pushing harder, right? Because it's lower. So the gas is higher pressure. So in this case, the pressure of the gas is greater than the pressure of the atmosphere, right? Because it's pushing harder. Over here, the atmosphere is pushing harder. So in this case, the pressure of the gas is less than atmospheric pressure, right? That's the gut factor with manometers. Now we can do the math. We can correct for it. Would you agree that in this case, the gas is higher pressure than atmosphere? So if we measure the atmospheric pressure with a barometer, we just add a correction factor, an adjustment to this. You ready? So let's take a look at it. Would you agree? Let's do this in black. If we look at the height difference, let's call that delta P, right? As long as everything's mercury, let's call that delta P. We can measure that height difference in millimeters mercury. Oh, so that would mean the pressure of our gas would be atmospheric pressure, and it's higher, plus that correction factor of that height difference. Makes sense, right? So let's say, the atmospheric pressure was 762.5 millimeters mercury, and you measure this height difference, and that's, 10.8 millimeters mercury. Add them together. That's the pressure of your gas. Easy peasy. Piece of cake. Not parcel of cake. Piece of pie. Piece of Rice Krispie bar. Over here, our gas is less than atmospheric pressure. Okay, so let's look at the delta P. Sound effects optional. But now it's a delta P in the other direction because we know our gas is less than atmospheric pressure. So the pressure of our gas will be the pressure of the atmosphere minus the height difference, as long as it's in millimeters mercury. Now, in lab, we're going to run into one scenario, and I'll show you how to correct that in lab, where we're going to be using tap water, I think, here, which is a different density. So we're going to have to measure the temperature of it, figure out the density of it, and make a correction for if this is a height difference in water, right? That's not going to be the same as in millimeters mercury. So if we're measuring the barometer in millimeters mercury, we have to convert the delta P in millimeters of water to an equivalent in millimeters mercury, which is going to be a lot lower, right? And then I can add apples to apples, right? So watch out if you're using any liquid other than mercury. But manometers are pretty cool. I mean, I'm not even going to do an example, right? Just measure that height difference, subtract it if your gas is less pressure, add it if your gas is higher pressure. And just based on the difference, who's pushing harder, the gas or the atmosphere? Let's get into the gas laws.